I want you to just imagine looking at a brand new photograph for a second. This image, it was actually captured just days ago, right in July of 2026.
Oh, yeah. That picture it's honestly stunning.
It really is. In the center of the frame, you've got this rugged, gray, just heavily pitted mass. And it's floating against this absolute black void of space. It looks incredibly lonely and, ancient. But here is the really fascinating part. You are looking at a celestial neighbor that we barely even knew we had.
Right, and I think that image really strips away this comforting illusion we have. Like, we tend to think our local planetary neighborhood is this fully mapped, static environment, but it's a striking visual reminder of just how much is still hidden right in our immediate vicinity.
Yeah, exactly. Because when most of us look up at the night sky, we see the moon, maybe we spot Mars or Venus on a clear night, and we just assume we know the whole cast of characters. But today we are taking a deep dive into some really incredible insights gathered from a recent breakdown by Anton Petrov.
A great breakdown, too. Lots to unpack.
Definitely. And our mission today is to explore that very photograph. We're going to examine the first ever close-up image of Earth's quasi-moon, which is a rock named Kamo'oalewa. We'll also unpack the actual mechanics of China's Tianwen-2 mission, because they're attempting a highly complex maneuver to grab a piece of it right now. And then we'll dig into this fierce scientific debate about where this object actually came from.
Which is a huge debate, by the way. I mean, the stakes for figuring out that origin story are surprisingly high. The answer could literally force us to rethink the history of our own planet and the moon.
Totally. So if you're the kind of person who loves a good scientific mystery, and you want to understand the actual nuts and bolts of how we explore the solar system, this deep dive is going to reveal a cosmic neighborhood that is highly dynamic and just constantly exchanging material.
Yeah, it's not a quiet place out there. But, to really appreciate the challenge of the Tianwen-2 mission, we first kind of have to understand the specific physics of its target.
Or the rock itself.
Exactly. So the object is formally designated 469219 Kamo'oalewa. It was discovered by the Pan-STARRS telescope back in 2016, I think. And the name actually comes from a Hawaiian chant that refers to an oscillating celestial object.
Which is, frankly, a remarkably accurate description of how it moved.
Yeah.
But we should probably also establish the scale here, because the term quasi-moon, it might conjure up an image of something massive, right? Like something pulling tides and lighting up the sky.
Sure, but it's actually tiny.
Yeah, it's estimated to be somewhere between maybe 15 and 100 meters across. So we're talking about a rock roughly the size of a modest office building just kind of tumbling through the dark. Earth actually has 8 of these confirmed quasi-moons, but Kamo'oalewa's orbital dynamics are, well, they're wonderfully counterintuitive.
Okay, let's unpack this for a second.
Go for it.
Because your first assumption is always that a moon orbits a planet, right? Like a true moon is gravitationally bound to its host. If Earth were just plucked out of the solar system, our moon would go flying off on a completely different trajectory with us.
Right, it's tethered to us. But Kamo'oalewa, however, is gravitationally bound to the sun. So the best way I can visualize this is, think of a high school running track. Imagine Earth as a runner in lane 1, just jogging around the track, which represents the sun at a very steady pace.
Okay, I like this.
Now, Kamo'oalewa is a second runner who enters the track in lane 2. They aren't tethered to the first runner in any way. They're just running their own race. But they happen to be running at the exact same speed, pacing the runner in lane 1 perfectly. So it feels like they are together.
That is a great analogy. It perfectly illustrates what astronomers actually call a 1.1 mean motion resonance. Kamo'oalewa takes almost exactly 1 Earth year to complete a lap around the sun, but because its orbit is slightly elliptical and a little bit tilted compared to ours, from our vantage point on Earth, it appears to loop around us.
Right, it looks like it's orbiting us.
Yeah, it looks like it's oscillating back and forth in the sky, even though we are basically just both orbiting the sun together.
And out of all the 8 quasi-moons we've identified so far, Kamo'oalewa is really the standout. It has been performing this, synchronized pacing maneuver with Earth for at least a century. And the orbital model suggests it's stable enough to stay in this lane for centuries more.
And that stability is exactly what makes it an incredibly tempting target for exploration. I mean, you have a building-sized rock. It's maintaining a consistent proximity to Earth. It sounds like an ideal candidate for a sample return mission, right?
On paper, yeah.
Right. But what's fascinating here is that the physics of the rock itself introduce a massive complication. Kamo'oalewa spins completely on its axis once every 28 minutes.
Every 28 minutes. I mean, let's just think about the mechanics of that for a second. A 50-meter wide boulder completing a full 360-degree rotation in less than half an hour. That means the centrifugal forces at its equator are intense.
Oh, absolutely. Material on the surface is just constantly on the verge of being flung off into space. Right. And that rapid spin, it dictates everything about how humanity has to approach this object. You cannot just casually drop a standard lander onto a surface moving like that.
Right. You just get swatted away.
Exactly. The rotation transforms what would be a simple landing into this unprecedented feat of orbital engineering, which I guess brings us directly to the architecture of China's Tianwen-2 mission.
Yeah, and the timeline alone shows how methodical this has to be. Tianwen-2 launched back on May 28th, 2025. And it couldn't just take a straight shot at the rock either.
No, orbital mechanics don't really allow for that.
Right. It had to spend over a year covering roughly 1 billion kilometers, just carefully adjusting its trajectory so it could slide perfectly into that resonant orbit by July of 2026, which is where it is right now.
Yep. Now that it has arrived, it is holding a safe standoff orbit about 20 kilometers away from the object. And just from a cosmic perspective, 20 kilometers is basically a hair's breadth.
It's incredibly close.
Very close. From that distance, it's going to spend the next 9 months conducting this high-resolution remote sensing study. So it relies on laser altimeters and optical cameras to map the topography. It's essentially building a highly detailed 3D model of this spinning rock to understand its center of mass and any gravitational anomalies.
Because all of that mapping is really just preparation for the main event, right?
Right.
T12 isn't just an observation platform. It's equipped with 3 different sampling methods, kind of escalating in complexity, to bring a piece of this rock home.
Right. They have backups for their backups.
Exactly. The first is a touch-and-go maneuver where the spacecraft swoops in, briefly touches the surface with a collection pad to kick up and trap some loose dust, and then immediately backs away.
And then the second method requires the spacecraft to actually hover. It'll descend close to the surface, utilize its thrusters to maintain a fixed distance relative to that tumbling ground below, and then deploy a robotic arm to physically scoop up the regolith.
Okay, and I understand how hovering works in theory. But the third method, this anchoring and attachment phase, is where I have to push back a little on the mechanics.
Oh, sure. It sounds like sci-fi.
It really does. I mean, wait, if we just establish that this object is the size of a small building and it's spinning like a top every 28 minutes, how exactly does the spacecraft physically fly up, fire a spike into it, and tether itself without getting violently wrapped around the rock or just instantly flung away?
It's a great question. The mechanism behind it is fascinating, and it all relies on relative velocity. Think of mid-air refueling between 2 fighter jets.
Okay.
The tanker plane isn't sitting still, right? It is flying at hundreds of miles per hour. But the receiving jet accelerates to match that exact speed and heading. So relative to each other, they're perfectly motionless.
Ah, okay. So the spacecraft isn't just hovering in one spot while the rock spins under it. It actually enters a synchronized rotation with Kamo'oalewa.
Precisely. Tianwen-2's autonomous guidance and control systems will fire its maneuvering thrusters to match the exact rotational velocity of the asteroid. So as the spacecraft descends, the rock below will appear to just stop spinning from the probe's perspective.
That is wild.
It is. And once that zero relative velocity state is achieved, the margin for error is incredibly thin. But that's when it fires a kinetic spike down into the surface.
And that spike physically embeds into the rock, serving as basically an anchor point.
Yes, exactly. The spike penetrates the regolith, and then a specialized claw mechanism secures the spacecraft to the surface. By anchoring itself, Tianwen-2 can counteract those intense centrifugal forces trying to throw it off.
Wow, okay.
And this allows its drills to penetrate beneath the space-weathered exterior and collect pristine subsurface samples. And it's worth noting, no mission has ever anchored to a small body using this specific kinetic tethering method before. It's a historic first.
That is incredible engineering. So once it successfully grabs those samples, the probe will detach and eventually depart in April of 2027. It's then going to perform a flyby of Earth later that year, dropping a return capsule containing at least 100 grams of Kamo'oalewa material for scientists to retrieve.
Which naturally raises the question of why 100 grams of material justifies a billion-kilometer journey, a multi-year timeline, and this unprecedented, highly dangerous anchoring maneuver.
Yeah, we are putting a whole lot on the line for what basically amounts to a small handful of dirt. But that handful of dirt might solve a massive scientific debate, because Kamo'oalewa is currently the subject of a pretty severe identity crisis. Telescopes have given us two very different hypotheses about what this rock actually is. So what does this all mean?
Well, let's start with the moon hypothesis. A few years ago, ground-based telescopes conducted spectroscopic analysis on the object. And just as a refresher, spectroscopy involves looking at the specific wavelengths of light that bounce off the surface of something.
Right, because different minerals absorb and reflect different wavelengths.
Exactly. It creates a unique optical signature. And the initial data from Kamo'oalewa showed a signature that didn't look like the typical asteroids we usually see near Earth. It actually closely resembled lunar regolith, specifically the soil on our moon that has been heavily altered by space weathering.
And space weathering is a crucial factor here, right? Because the surface of the moon is just constantly bombarded by solar wind.
Right, which is largely high-speed hydrogen ions plus micrometeorites. And over millions of years, this bombardment literally melts the microscopic outer layer of the soil grains.
Wait, it actually melts them?
Yeah, it melts them and precipitates these tiny droplets called nanophase iron. These iron particles absorb visible light and reflect near-infrared light, which shifts the object's overall optical signature toward the red end of the spectrum. Kamo'oalewa showed exactly this red-end signature.
Leading scientists to hypothesize that this isn't just some random asteroid that wandered in from deep space. The theory is that it is a chunk of our actual moon.
Yeah.
Like a massive impact, likely the one that formed the Giordano Bruno crater a few million years ago, hit the moon with enough kinetic energy to blast a fragment completely out of lunar orbit.
And the physics of that Giordano Bruno impact perfectly support this. The ejecta would have had enough velocity to escape the moon's gravity, sure, but not enough to escape the inner solar system.
So it just gets stuck out there.
Exactly, placing it in a resonant orbit around the sun, perfectly pacing the Earth.
I mean, it is an incredibly elegant theory. Just think about it. A piece of the moon, violently evicted, coming back to pace a century after century. But then the James Webb Space Telescope recently looked at Kamo'oalewa and complicated the picture entirely.
Yeah, JWST really threw a wrench in things, because its infrared sensors are exponentially more sensitive than ground-based telescopes. So when they analyzed the rock's spectrum, the data indicated the surface was actually less red and a lot more neutral than previously thought.
Which totally undermines the lunar origin theory.
It does. It introduces the strong possibility that Kamo'oalewa might just be a standard stony asteroid. It could be an L-chondrite, which is a type of meteorite with a low iron content, or an S-type silicious asteroid, or an E-type enstepite asteroid.
Right. Those are all classifications of primordial rocky bodies. Right. Leftovers from the formation of the inner solar system.
Exactly. The JWST data suggests Kamo'oalewa could simply be one of these super common rocks that just happen to drift into this unique orbit. And it only partially mimics lunar soil because it's experiencing the exact same solar wind weathering that the moon does out there.
So we have a direct conflict between two sets of optical data, which perfectly illustrates why we need those physical samples. I mean, telescopes can only analyze the light bouncing off the outermost layer of dust. You can't put a photograph into a mass spectrometer?
Well, if we connect this to the bigger picture, bringing those 100 grams back to a terrestrial laboratory changes everything. Because scientists will use mass spectrometry to look past that surface weathering and examine the object's actual isotopic signature.
We should probably explain how that works, because isotopes act as this, undeniable chemical fingerprint.
They really do. So elements like oxygen come in different forms, or isotopes, depending on the number of neutrons in their nucleus, like oxygen 16, 17, or 18. And the ratio of these isotopes is highly specific, depending on where an object originally formed in the early solar nebula.
Right. And the Earth and the Moon share a nearly identical, very distinct isotopic ratio.
Exactly. While asteroids that formed elsewhere in the solar system have completely different ratios.
So a mass spectrometer basically takes a tiny piece of the sample, vaporizes it into a gas, and then uses these powerful magnetic fields to curve the charged atoms. The heavier isotopes, they curve slightly less than the lighter ones, which allows scientists to just count them and calculate the exact ratio.
And that ratio will provide the definitive answer. If the isotopic fingerprint matches the Earth-Moon system, boom, we have proof of an ancient lunar impact. If it matches known chondrites, it's just an asteroid. The isotopes are immune to surface weathering. They will tell us exactly where this rock was born.
Solving the origin story of Earth's closest stalker feels like a complete mission in itself. But Tianwen-2's journey does not end when it drops that sample capsule into Earth's atmosphere in late 2027. It actually uses the momentum from that Earth flyby to slingshot itself deep into the solar system toward a second target.
A target that it won't even reach until January of 2035. This second phase represents China's first long-term deep space exploration mission beyond the Earth-Moon system. And the target, which is designated Comet 311P, is incredibly bizarre.
Bizarre is definitely the right word. When the Hubble Space Telescope observed 311P, it revealed an object that does not look like a standard comet with just a single glowing tail. It has 6 distinct sweeping tails.
Yeah, and the mechanism generating those tails really challenges our standard definitions. I mean, a typical comet is often described as a dirty snowball, right?
Right.
As its orbit brings it closer to the sun, the solar radiation heats it up, causing the internal ice to sublimate, meaning it transitions directly from a solid ice into a gas. And this off-gassing blows dust and material into space, forming that classic tail.
But 311P's multiple tails are not caused by melting ice.
No, they aren't. The current understanding is that 311P's tails are a product of centrifugal disintegration.
Okay, what does that mean exactly?
Well, a lot of small asteroids are not solid monolithic boulders. They're what we call rubble piles, so they're just loose collections of rocks, gravel, and dust held together by very weak mutual gravity.
And just like Kamo'oalewa, 311P is a very fast rotator.
Extremely fast. When a rubble pile asteroid spins faster than once every 2.2 hours, the centrifugal force at its equator actually exceeds its own gravitational pull. So the internal friction is no longer enough to hold it together. The asteroid literally begins to fall apart. Boulders, pebbles, and dust just effortlessly lift off the equator and float out into space.
Here's where it gets really interesting. So 311P is spinning so violently that it is literally shedding its own mass. And the pressure of the solar radiation catches that drifting debris and stretches it out into those 6 incredible cometary streams.
Exactly. And there are even observations from 2018 suggesting a large piece might have broken off entirely and is now orbiting the main body as a tiny moon.
That is wild.
It is. And that potential binary nature is a key reason Tianwen-2 will enter orbit around 311P in 2035. Because by studying a rocky asteroid that is tearing itself apart and mimicking a comet, scientists can explore the continuum between these celestial objects.
Right, because we tend to rely on these neat binary categories.
Yeah.
Comets are icy bodies that sublimate, asteroids are dry rocks that don't. The 311P proves that a dry rock can behave exactly like a comet if the rotational physics are just extreme enough.
It forces us to view the solar system not as a collection of isolated categories, but really as a fluid spectrum of physical processes.
Yeah, and I think pulling all of these insights together, the most profound takeaway from this deep dive is how active our local space environment truly is. We are not traveling through a static clockwork void. We live in a violently dynamic neighborhood where, solar radiation alters chemistry, centrifugal forces tear mountains into dust streams, and gravitational resonances capture wandering debris.
It highlights a concept astronomers often refer to as the planetary billiards game, this continuous, chaotic exchange of material across millions of miles.
And that concept leaves us with the fascinating kind of lingering thought based on Anton Petrov's notes regarding the exchange of material in our neighborhood. I mean, if the mass spectrometer proves that Kamo'oalewa is indeed a piece of the moon violently blasted off by a meteor, tumbling through the void for millions of years, only to end up locked in a century-long dance alongside us, what else is out there?
Oh, it completely reframes how we think about ancient impact events on all planetary bodies.
Exactly. Think about the asteroid impact that wiped out the dinosaurs. That collision ejected billions of tons of Earth's crust into outer space. So could there be chunks of ancient Earth pieces of our own home from 65 million years ago currently drifting through the inner solar system? Is it possible that a fragment of Earth is out there right now, masquerading as an ordinary asteroid, perfectly pacing the orbit of Mars or Venus as a quasi-moon? The physical mechanisms we discussed today prove that it is entirely possible. The planets and moons might be quietly trading pieces of themselves across the solar system. And I think the next time you look up at the night sky, you really have to wonder whose history is floating past us.